Welcome to The Explainer. Today, we are diving into one of the absolutely strangest forces in the universe. It's a force that comes from a place we all think of as completely empty, but it's so powerful it might just shape everything, from the tiniest bits of nanotechnology all the way up to the fate of the entire cosmos. So let's just start with a really basic question. You take a box and you suck everything out of it, all the particles, all the dust, all the light, everything. What's left? Is it just nothing? Well, for centuries, the answer was, yeah, of course, it's nothing. But quantum field theory completely flips that on its head. It tells us that the vacuum of space is anything but empty. It's actually this seething, bubbling cauldron of energy, with these so-called virtual particles flashing in and out of existence faster than you can even imagine.
Okay, so if that's true, if empty space is actually buzzing with energy, then that leads to a really cool question. Can that energy actually push on things? Can it exert a real physical force on objects in our world? This idea is called vacuum energy. And maybe the best way to get your head around it is to stop thinking of space as empty. Instead, picture it as being filled with this invisible grid of tiny balls connected by springs. Even when it's totally quiet and in its lowest energy state, what we call the vacuum, that grid is still vibrating. It's still humming. That background hum is vacuum energy.
Now that is a pretty wild idea, right? So how on earth could you prove that this force from nothing is actually real? Well, the answer comes from this really clever experiment, which was predicted decades before anyone could possibly build it.
And the logic is just brilliant. Okay, so think of all those vacuum fluctuations as energy waves of all different sizes, all bouncing around. Now, imagine you take two perfectly smooth metal plates and you bring them incredibly close together. You've just created a tiny little space between them. And here's the trick. Only the waves that can perfectly fit in that little gap can exist there. All the bigger waves are excluded. That means you've got more waves, more energy pushing on the outside of the plates than on the inside. And the result? The outside pressure literally shoves the plates together.
And this wasn't just some idea on a chalkboard for long. A physicist named Casimir predicted all this way back in 1948. But the force is so tiny and the experiment is so ridiculously precise that it took almost 50 years to actually measure it. Finally, in 1997, an experiment proved it. The Casimir Effect was real.
And don't let the word tiny fool you into thinking it's weak. It's not. At normal distances, you'd never notice it. But if you could get those plates to within just 10 nanometers of each other, that's about the width of 100 atoms, the force from nothing creates a pressure that's equal to the atmosphere of our entire planet at sea level. That's a serious amount of force, all from empty space. So, this is great. We prove vacuum energy is real, it's powerful. Case closed, right? Well, not so fast. Because this is where the story takes a sharp turn. When scientists tried to apply this idea to the whole universe, they didn't just find a small problem. They stumbled onto what might be the single biggest crisis in all of modern physics. You see, according to Einstein, every single form of energy has gravity, and that includes vacuum energy. So if you do the math and you add up all the vacuum energy that quantum theory says should be out there, its gravitational pull should be so unbelievably immense that the entire universe should have collapsed in on itself a fraction of a second after the Big Bang. We shouldn't be here.
And when I say immense, I want you to really try to picture this number. Our best theories predict a level of vacuum energy that is bigger than what we actually see by a factor of 1 followed by 120 zeros. It is so wrong, it's often called the worst theoretical prediction in the history of science, period.
This massive epic failure is called the cosmological constant problem. On one side, you have the theory, which predicts an energy so big it would crush everything. And on the other side, you have our actual observations of the cosmos, which show a teeny tiny amount of energy, what we call dark energy, that's gently pushing the universe to expand faster. The two numbers couldn't be more different.
So, what gives? How do we fix a problem that's off by 120 orders of magnitude? Well, a really radical new idea suggests the answer comes from something deep in the heart of quantum mechanics itself, the link between what's real and what's measurable. So let's break this down. The core idea is, what if not all vacuum energy actually creates gravity? What if it only becomes gravitationally active, what if it only contributes to dark energy, if we can actually detect it? To put it simply, if you can't measure it, it doesn't gravitate. And here's the thing, we can measure it. This graph right here is the proof.
The data points are from a special device called the Josephson junction. You see the curved line? That's the total electrical noise it's picking up. But look at that flat part at the bottom. That's the key. That's the constant underlying hiss of the vacuum itself. We can literally listen to the buzz of empty space.
Now, this whole measurement creates reality idea isn't just a philosophical get-out-of-jail-free card. It makes a real, concrete prediction that connects an experiment you can do in a lab directly to the dark energy that's running our entire universe. So these detectors, these Josephson junctions, they're made out of superconductors. You can think of them as these perfect quantum microphones, sensitive enough to hear the faintest whispers in the universe, including that constant hum from vacuum energy. But, like any piece of high-tech equipment, they have a breaking point.
Here's the catch. A superconductor only works if it's super cold. If it heats up past a certain critical temperature, it just stops working. And that temperature limit creates a hard physical cutoff on the frequency of the vacuum waves that the device can hear. It can't hear anything higher than that. And based on the physics of the best superconductors we know how to make, this hypothesis predicts a specific cutoff frequency. It's about 1.7 terahertz. Any vacuum fluctuations happening faster or at a higher frequency than that are basically invisible to us. They become fundamentally unmeasurable.
And this is the absolute kicker. If you make the assumption that only the measurable vacuum energy actually has a gravitational pull, if you add up all the energy from the lowest frequency up to that 1.7 terahertz cutoff, and you just ignore everything above it, the final number you get for the energy density of space is an almost perfect match for the amount of dark energy we actually see in our universe. It works.
So what does this all mean for how we see the universe? Well, it paints a completely new and kind of staggering picture of reality.
Well, for one thing, that cosmological constant problem, the 10 to the 120th power error, it just goes away. All that other energy is still there, it's just gravitationally silent because we can't measure it. And it means the amount of dark energy driving the cosmos isn't just some random number. It might be directly determined by the fundamental properties of superconductors, by the very physics that allows us to see it in the first place.
And that leaves us with this one final, pretty profound question. It suggests a universe where reality on the biggest possible scale might be tied directly to our ability to observe it on the smallest. Maybe the thing that truly shapes the cosmos isn't just what exists out there, but what is, even in principle, knowable.